can get the page to change. There we go. God bless you. Number 3. So, look at number 2 first. Here is the answer here to number 2. Oh, I took number 3. Where'd my number 2 go? Oh, sorry. There's the answer. It did change. Very good. All right. So, to do this, again, you want to solve for this equation here as written. So the 285.8 needs to be doubled to get 2 moles up here at the top. The delta H for this equation, okay, as written, you add up the first delta H, the second one, and the third one. You'll notice that this equation here had to be what? It had to be reversed. The top equation had to be multiplied by 2, and the middle equation was good the way it was written. So when you rearrange it, doubling it, reversing the equation, here you get your CH3OH, your O2s, you have one O2 left over on the left, your H2s, you've got 2 H2s left on the left, 1 C. Everything else should cancel. So just to make sure, if you set it up right, everything else should cancel. So we've got our 2 waters on the right. They cancel out the 2 waters on the left. The CO2 gas on the left cancels out the CO2 gas on the right. Methanol doesn't cancel. You have 3 halves O2 on the right and 2 O2s on the left. So that leaves you with a 0.5 O2 left over as those cancel out. You've got carbon on the left, you've got 2 hydrogens on the left, plus a half of oxygen. So here's our left side of the equation, and our right side of the equation is just the methanol. Yes? How much of the work do you have to show? So on something like this, let's see what they would want. They want the delta H for this particular reaction. So what they would want to show to give complete credit for it is you would want to show all those equations would have been given to you. So what you would want to show is you want to show the equations written. You would also probably want to show them canceling out, and then show that these 3 are being added up. So you could do just a plus sign here. You don't have to do this whole thing here again. It was just done on this because it was a computer. It was a little easier to show that. But you add those up. It's an easy way of showing it. You make sure you show the final equation here, or by crossing it out, it shows the final equation. So there's a few options on how to show that. Some people like to show this, but you have to show where these numbers, why you did what you did. So reversing the equation shows why you had to have positive 7.6 there.
Can we just draw an arrow above and like cross out stuff and not?
You just flip the arrow and flip the sign. I think that would be acceptable. Trying to remember what it would look like. Yep, you'd probably be able to do that. Yep, so you don't have to rewrite the whole entire equation. That would save time. Yep, but you do have to show, everything obviously being changed and what you have to multiply by. So showing the math portion of it and showing why it adds up. If you did just that, you might want to show where you got your answer from, like this step. If you just were drawing and you didn't have the whole thing drawn out, you just rearrange things. That would be for complete credit on something like this. So yeah, that would make sense if they gave you the equations and they gave those to you before a pre-response question. Okay, the next step is a reaction with C2H4 and oxygen. So in this reaction here, you're going to want to do what it says on here. You've got a little less than 4 minutes on this one, but we'll start with 4 minutes and see how we do. You may begin. look at question number 3 here. All right, so on question number 3 here, what is the equation? What is the equation? Equation, yes, sir. Okay, Q equals MC delta T. All right. Now, the mass. The question is, what mass do we use? Do we use the C2H4 mass or the water mass? Water, because we got to do Q from the water's point of view. What do we do with this? I would have to look and see. Yes, you would. At the end, you will need to convert, when you get your joules per mole, you have to convert grams into moles using the 6.26. That's the final step. So let me show you how to go about this. Your Q of the water's point of view. You can't measure the temperature of the C2H4. You're almost always doing calorimetry from water's point of view. Heads up on that. So 1,000 times the specific heat capacity times the change in temperature gives us the Q for the water. Now, the interesting thing is the Q for the water is equal to the negative for the heat of reaction. Why is that? Why is this just the opposite sign of that? Yep.
Because the heat given off by the reaction is the heat absorbed by the water, so they're equal in the opposite way.
Excellent. Very good. Negative sign. Does negative sign mean exo or endothermic? Okay. Negative sign means heat is going out of the system. Positive sign means heat is going into or endothermic. So the reaction is an exothermic reaction. And how else might you know that? Well, you're combusting something. When you light a fire, it usually gives off what? Heat. Usually, meaning every single time. But that's still usual, just to make sure you were clear on that. So that's a hint on the sign. We got this. This is the negative value of that. Then we have to convert the 6.26 to moles. Where do we get this number from? Molar mass. Very good. Periodic table, molar mass of C2H4. And then we take this number and divide it by the moles. That gives us the joules per mole. And if it wanted the answer in joules per mole, that's all we had to do. And it's per mole of C2H4 because that was the fuel. Yes? Okay? So, the reason it's negative, in part, think about it, we've got water here, and we've got our fuel. Now, it doesn't tell us where our fuel is, but I'm going to draw it as a box just to make it really easy. So, this is our fuel. Our fuel is combusting. It's going through a reaction. And the water's temperature does what? So the water's temperature goes from 22.6 up into 93.2. So the water temperature is going up. So that means it must be absorbing heat. So it's going that way. The direction of heat is going from this to this. So the water is absorbing the heat. It's positive. This is losing the heat to the water, so its delta H is negative. If it's a calorimetric problem, yes. So if the water's temperature is going down, that means the opposite is happening. Energy is going into the system. And so this could happen a lot of times on the AP test, not always, but when they're dealing with thermodynamics, is they like to do this because people often know this. This one is a little bit different. You have another chemical like NH4Cl, ammonium chloride. This causes the water temperature to go down, so the water loses heat, and this gains heat. But the temperature goes down. So that's a common, well, not a common, but it's one possible You've got this, you know this, you just flip it around, you've got a different reaction. So endothermic reactions or exothermic reactions, you could do it either way. So we've got 3 sig figs here due to the degrees Celsius. Yes? Grams to moles. Grams to moles, we've got 3 sig figs here. Yes, this value here is more precise than it needs to be. You don't want to round until the very end. So this is more precise than it needs to be, which is good. This is more precise than it needs to be. And then your final answer, well, this had 3 significant figures originally, the grams, so that limits it to 3, plus the degrees Celsius happens to limit it to 3. Do not round until the very end is the moral of this problem story for sig figs. Yeah?
So they only grade sig figs on the final box?
Yes, if it's asking for the answer, whatever the answer they want. Okay. If they wanted this answer, you would have to do that in sig figs.
And then would the final answer also be slightly different then?
Nope. You have to use this to continue on. They don't tend to do that much in chemistry. They ask for one specific thing, but if they did, for some reason, say, hey, what's this? That's a problem. You would have to write the answer with sig figs. But you would have to use your original data if they asked you to continue on.
Oh.
Okay? So you don't use the previous rounded answer at any time for a future answer. It's kind of it becomes less precise, and you get variety of answers. So the rules in significant figures are that everybody gets the same answer. So that the chemistry graders all have the same answer to grade. You don't have to consider uncertainty. Yes?
For the midterm, will you get marked off each problem if we go to sig figs, or will be 1 point for the whole FRQ section of a midterm?
How about you use significant figures and don't worry about it? You won't get double penalized for making the same dumb mistake more than once. But you could get penalized on multiple problems for making the same mistake, like using no significant figures. So on one problem, if it has multiple parts, you may not lose -1 on every single problem. Yeah. On the AP test, they decide when they take points off for significant figures and when they don't. And you never know when it's going to happen, unless you can predict the future. So if you don't use them, a problem can be worth 1 point, and that's all significant figures, even though you had to do this big old calculation. So you do all this work and you get 0 points. It's like, yeah.
But if you put in the factor power, you just add it.
If you had to consider that, yeah, you would have to have a bigger Q equation to consider that, like we did in the lab. Yep. Yep. No. So standard enthalpy change means it's happening under standard conditions, standard pressure. So it is assuming that that you don't have any work being done. If it's not standard conditions, you got to consider the work part. Pressure times delta. Yes. Yep.
On a test, if there were multiple parts, and you got like part A wrong,
Yep.
and then part B wasn't dependent on part A,
Yep.
does that mean you lose part B's points too?
No, you can always assume an answer from a previous problem and get full credit. So even though they are based on each other, so it makes it easier if you sig figs. If you make a mistake in one place and you keep using those same numbers, the grader will have to give you credit for what you did do and not what you didn't do. But it's still not something that's advisable to do if you can avoid it. All right. The next question. 4 minutes for this. All right. This is using. This is using the same reaction. As you can see here, the same chemical reaction. same chemical reaction, but this is information about the substances involved in the reaction represented above is summarized below. So there is no letter A technically, but letter B, I'd like you to calculate the bond energy of the bond present in O2 from the data provided. All right, let's check our answer here. So delta H of the reaction from the previous problem was negative 1323.67 kilojoules per mole. If you did it in joules per mole, just make sure you convert. Yeah. Because if you look at the bond energies here, bond energies are in kilojoules per mole. So if you're solving for something, you want it to be in kilojoules per mole.
But why can't you just use like 1?
You would either have to multiply all of the values times 1,000 and then convert back at the end. Or if you convert it to kilojoules per mole first, with the delta H of the reaction, it'll save you quite a bit of work. All of the numbers up there are in kilojoules per mole.
No, I mean like why can't you use 1320, like the sig fig number? Like
We talked about that earlier. If you use the sig fig number, you are rounding. What I do is I write down what my calculator tells me, and then I press a almost equal to, and then write the sig figs as the answer. So I always have that number up there. Don't recalculate it. So let's say we had this problem here, for example. Okay, you got your calculated value here. If you show your work, you have that number written there. What I do, just as a convenience, and because they constantly ask you to go back to problems, is my equals is negative 1323670.9 joules per mole. Then, when you round to significant figures, you are finding a number that is not quite equal to that, based on the rules of significant figures. So it's approximately equal to the 1320, and you've got 3 more zeros, joules per mole. Right? What one? Where's my one? There we go. So this number here you wrote as 1.32 times 10 to the 6 joules per mole. That's the answer that they wanted for the previous problem. But you'll notice I have the calculator answer already here, so I can reuse this at any time. When you're dealing with thermodynamic problems, they like to do them together. They like to have them rely on previous information. That's to save you a little bit of time. But if you want to recalculate it, go for it. So that's why, and then you convert to kilojoules per mole, that's here. The delta H, you got the energy of the bonds broken, the reaction, the delta H of the reaction is equal to the Bond energy of the broken bonds minus the bond energy of the formed bonds. And you've got everything except the O bond there. Because there's 4 C-double-O bonds in, there's 2 CO2s. So here's our 1 CO2 and our second CO2. Some people like to draw structures on this because it makes it easier to count the bonds. Yes? Use the chart on the right? Ah. Could you use the chart on the right? Well, the only problem with the chart on the right is it doesn't have water in it. You could find water with what? So when you're using bond energies, you want to use bond energies only. When you're using heat of formation, you use heat of formation. The major difference, this is something that is a slight difference but makes a big deal. This equation up here is for bond energies. Okay, for bond energies only. Okay, if you're using Hess's law for heat of formation, again, the idea is the same, but it is written a little differently. Hess's law, the delta H of a reaction, is equal to the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants. So heat of formation data, say you take the products data minus the reactants. Heat of formation data is kind of the opposite of the bond energy, kind of, but it's not the same. Bond energy is an average of all the bonds. Heat of formation data is usually from experimental results or from tables that are experimentally designed. So usually when people want a heat of reaction, they can get it this way. If you want to know the bond, though, you take your heat of reaction you got, and you then solve the equation for a particular bond. So some people, there's many ways of thinking about this. Bonds being broken. Some people even say bond energy is kind of the opposite order. Because bond energy is always positive, heat of formation, delta H of formation is usually negative. So if you think about them in an opposite point of view. What's happening in a reaction is we start with our reactants. Okay, they're going to products. And what's happening with this is the first thing that's happening is bonds are being broken. And then bonds are being formed. Going from reactants to products is our delta H for the entire reaction. So you can either think of it as everything being formed, the formation, which is the opposite of breaking. So it'll have the opposite sign. So that's why you could not, unfortunately, use the heat of formation data. So that was part B. So the last part is to use that data that's provided. So you're going to write the you're going to do C and D at this time. You've got less than 4 minutes. So on your mark, get set, start. All right, in just a moment, we're going to look at how to do C and D here. reaction to form the products minus the heat to form the reactants. The reason it's minus is you're not forming, you're breaking apart the reactants and you're forming the products. And don't forget, it's the same reaction as it was before. Same reaction, same reaction, same reaction. All right, ladies and gentlemen, let's look at these two here. All right, these two. The first one is to write the standard formation equation for H2O gas. So you want to form H2O gas from its elements. That's what heat of formation means. So what are the two things that make up H2O gas? Two elements? H2 and O2. Okay, that makes our H2O gas, but it's not balanced yet, right? So what do we have to do? Half the O2. That's it?
That was it?
That's it for C. Yeah, if you really should have the phases if you want to be perfect, which we all do. All right. So the next one, D. D is asking calculate the standard enthalpy of formation of H2O gas. So you want to find, I'll just write it down so I know what I'm looking for. I want to find the heat of formation standard of H2O gas. So to do this, we have an equation that's written up here. Same equation as before, right? And we want to use the heat of formation data. So we're going to use Hess's law with the heat of formation, which says that delta H is equal to the sum of the heat of formation of the products minus sum of the heat of formation of the reactants. So the delta H, okay, the delta H, I'm not going to plug that in yet, but now I got to look at the products. So I don't have the equation on this screen, so the products are H2O and CO2. So we've got 2 moles of CO2, so we need the heat of formation for CO2, plus we've got 2 moles of the H2O, and again that's heat of formation of H2O, pardon me. And then we want to subtract, this is 2, this is 2, 2 moles, pardon me, I didn't write moles in there because I was running out of room. That is careless. And then you've got the heat of formation of the reactants. First reactant is C2H4, there's 1 mole of that. So 1 mole times the heat of formation of the C2H4. And then I have how many moles of oxygen? 3 moles of oxygen. And I need the heat of formation of oxygen. And there is my equation. Now all I have to do is plug in the correct numbers. The thing I don't know, I'm going to have a variable for this, so I'm going to choose my favorite variable. C? M? Yeah, but then it gets really confusing because M is mass and C is the speed of light.
Yes, that would be so cool.
Chicken. All right, so I'm going to draw a little chicken. There we go, that's a chicken. All right, so I'm solving for chicken or hen or whatever you want to call it. So the delta H, oh wait, I already did the delta H. Don't get too far ahead of me. Delta H, I remember that. It's negative 1323.67. The delta H, same exact reaction, is negative 1323.67 if I copied it right. Kilojoules per mole.
What was 489.11?
Huh? 489.
489. What was that?
I don't.
Oh, that was for oxygen, huh? What was that?
Yeah, that was my oxygen answer.
See,
Yeah, it gets a little tricky. If you don't keep track of the numbers, that's my delta H. And then, yeah, coefficient is the moles. Now I've got 2 moles. I'm going to put 2 here times the CO2 value, which I look up on the table. Negative 393.5. And that's kilojoules per mole, just in case you wanted to know that. And then we add 2 moles of the unknown, which is my chicken. And then we subtract 1 mole, and then the C2H4, which is right there, 52.30. All right, plus, and this is my favorite thing. What the heck? They didn't give us the oxygen. No. Jerks. What do you know about heat of formation of an element? It's 0. Yay. So this is the heat of formation of oxygen is 0 because you're forming oxygen from its elements, and oxygen already is its elements. O2 is already O2. So it's 3 times 0, which equals 0, of course. Unless you mess that up. All right. So now all you got to do is make sure you type it correctly in your calculator, which is sometimes the hardest part. Oh, geez. Yeah. And I got a chicken over here. So, thinking crazy chicken. All right. So, I would rewrite this because I'm getting lost in all the chickens. So, kilojoules per mole. I know some of you are like, why did you do that? Minus 52.30 kilojoules per mole. And this equals 2 times that, which I might as well multiply out while I'm at it. 2 times negative 393.5. That's equals negative 787 kilojoules. Oh, that's kilojoules now. Plus 2 chickens. All right, and then you just solve for chicken. So 1323.67 negative. 1323.67 minus 52.30 plus 787 divided by dose. And if you do this right, you get a number for chicken. So chicken equals negative 294.485 kilojoules. And that's kilojoules per mole because you already divided by the 2. And let's see how we did. 294. Did I do the wrong chicken? Oh, yeah. Oh, yeah, I forgot about my negative sign. Yeah. This is a negative sign here. I forgot about it. That was my bad. So I should have added that together. That'll change my chicken to the correct value. Gotta watch out for those signs.
What's the correct value?
Correct value is negative 242.2. There's too much noise for my chicken to operate properly.
Chicken also turned into a blob.
Hey, just because my chicken turned into a blob. So, sorry. You got to keep track of your information any way possible. I have never drawn a chicken instead of an X, so it made me a little confused. Now, the key step, as you saw, my mistake was to not keep track of the signs. Oftentimes, you don't put a negative sign, you put it in the wrong place. A few of you did that in your Hess's Law Lab. You made it positive when it should have been negative, or negative when it should have been positive. You may not think it's a big deal, but it changes your answer, and guess what you would have gotten if you got the wrong answer? You get 0. You go, I did all that work forward.
Wait, you don't get any points for like.
You would hope that problem's worth 2 points, and you hope they give you something, but yeah. So you want to take your time. Take your time. You don't need to draw chickens, but you can take your time. All right. really quiet. Please stop talking, even if you have the most important question in your life. Christine has the floor, yeah?
Is it the same why O2 is like 0 and not 4?
Yes, I will explain O2. O2 is O2 in all elements. The cool thing about when you have heat of formation, this is something that is often or always put in a problem with heat of formation. It's something that you have to remember or you have to think about. Okay, so the heat of formation is defined as the energy to form a compound from its elements. So you want to form something from its elements. So if you want to form CO2, you're going to take C and O2 and put it together. You want to form H2O, gas or liquid, you got your H2 and your O2, and then you need the half, right? Well, what if you want to form O2? What's the elemental form of oxygen? O2. If you start with O2 and you end with O2, there's no change. You could even think and say, well, you separate them, then you bring them back together. Well, the energy to separate them and the energy to bring them back together will cancel out. So that's why elements are 0. So if you said, I wanted to know the heat of formation to form iron, well, iron's already iron, so it's going to be 0. It's defined as 0. Okay? Okay? Now, the interesting thing is, once you have that definition, if you wanted to form O is not elemental form. So if you want to form O, you have to make it from O2. Whoa, weird. This is the elemental form. This is not the elemental form. Oxygen by itself is extremely reactive, and that's why we have to remember the 7 at 7. 7 at 7 that are diatomic, those are the ones that are tricky, like nitrogen, oxygen, chlorine, fluorine, hydrogen, bromine, iodide.
Hydrogen.
I got hydrogen in there, hopefully. 1, 2, 3, 4. I did them out of order. 5, 6, 7. Dr. Hofbrinkel, 7 at 7. Christine, does that make more sense? So, and most of the time, you will not see elements in a table of heat of formation data. They don't include it, especially on the AP test.
Oh, it's so
It's always
confusing.
0. Actually, they write it down if it's always 0. They're never going to include it.
I thought you meant the other one.
Yeah, in some textbooks they will include it, but they're like, no. So, why do those textbooks include it? Because they use it to show the fact that they're all zeros. Now, as you can see in all these problems, you've got to use information as you gather it to solve the next problem. When you come across a problem where you're like, oh, garbage, I don't know what delta H is. Oh, D, oh my goodness. What the F? Oh, there's no F up there. So D, what's wrong with D? I can't find delta H. Where is it? I can't see it. It's not here. Calm down. Look at the reaction above. The chance of it being on a previous problem or part of a problem is a 99%. They don't usually put it in the multiple choice and then the free response. I've seen that happen on tests before, but on the AP test, haven't seen that mistake happen. Okay. Yes? Right, they would have to do it based on your previous answers. Yep. Yeah. So your calculation doesn't matter quite as much, but you still don't want to make stupid mistakes like signs or sig figs or, yeah. You want to try to avoid those as much as possible because the grader, the person grading this, they grade A, B, C, D. So if you get A wrong and you're not very good on A, and they are like, I don't like this, and they start marking points off, the interesting thing is the graders are humans. There's other people that will review it. But if the grader goes, this person has no idea what they're talking about in the first problem, they start not seeing opportunities for points. And if their grade is within the range, and somebody else agrees with them, then you might lose a few points that you could have gotten. So they're not trying to hurt you, they're trying to look for opportunities to give you points. But if they're grading these for 4 days straight and yours happens to be the next one that comes up, and you did something completely crazy on the first one, they might go, they have no idea what they're talking about. Of course, there's someone else that will read it that will go, no, 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 they do know, but that person's been there for 4 days as well. Just as a heads up. I'm just telling you the realities of the AP grading. It's really good because it's not just one person, like Mr. Christopher going, I made a mistake again and again and again. So that's a good thing. All right. Tomorrow, what lab are we doing tomorrow? 10, 10, 10, 10. Once you have it, bring it, put all your things away. If you've got any of these things at your table, please return them to the front and to the back. Kevin still here? All right. Yes, sir? What we did today? This is already online. I'll try to post the video as soon as possible, which will probably be tomorrow because I have to process it and post it on YouTube. But this is already online. It's under test review, and then there's 2 different test reviews for the midterm. One is review session, the other is review problems that they will review status. I do. You! I know what you mean. I know. Sabaya is able to do it differently than me. I know. What? These are the problems here. These are the problems here we did in class review problems. Okay. So this, yeah, I would definitely, if I were reviewing, I'd do all of them. This is the review guide that lists out the things you need to know and some sample questions here. So, yes, absolutely. Answer sheet. Yes. Oh, your lab. Did you turn in your lab, Hess's Law Lab, to me?
Hess's Law?
That's Lab 8. Lab number 8.
Yeah, there's a stripe on it.
Where is it? You have it?
You handed it back to us.
I need it back.
Oh.
The stripe just meant that it was turned in on time. I need it back to grade it.
Oh, okay. Oh, yeah, that makes sense. Is that
They are all graded. No. Sorry. You can see it's great online if you really want to.
Awesome title.
But I have to hand them back later. I like your title. I did see your title earlier.
Do you like the movie? Wait, do you know the reference?
Oh, Brother? No.
Yep, that's
Oh, it is? Good. I did like the movie very much. George Clooney does some very unique movies. And I actually...
I like the frog.
When I saw the movie, I saw it in the theater and I thought it was ridiculous. And I was like, what in the world? And then I enjoyed it more and more as it went on. And I didn't understand what was up with it. And he did another one with goats, I think. Goats and War or something.
Goats and War.
I can't remember what it was. It was so ridiculous. It was another one of those George Clooney ridiculous movies that was great and fun. What's up, MK?
My initials sound so cool. I just kind of realized that.
Your initials? Duh, that's your
MK.
email. You're so cool. MK, it's like Delta K, but MK instead. What's up?
I had a few questions. Okay, first, over here, are these all the names? Like, if we know this, are we good?
For atomic theory?
Just for like all the dates and names and stuff. As long as we know these, are we good? Or
These are the people that we learned about, yes.
okay, so as long